And that's what we're going to talk about today, because the sun is really important about our skywave propagation. And that's what I'm going to talk about. This is the lecture that I use in the general class. So we use the ionosphere for shortwave or HF propagation. And the ionosphere consists of three layers: the D layer, the E layer, and the F layer. And the D layer is closest to the Earth. It is the thickest layer of atmosphere. The E layer is the mid layer, and then the F layer is the highest layer. And as you know, as you go higher and higher, the molecules of gas get further and further apart. The F layer, the D layer can start as low as 30 miles above the Earth, and at that point, the gas molecules are far enough apart that ionization can occur. So what the heck is ionization? Well, that nuclear fusion reactor that we talk about, the sun, is spewing out ionizing radiation. Ionizing radiation, ultraviolet light, and it ionizes the gas molecules. So our atmosphere is made up of 79% nitrogen, 21% oxygen, and then just some various small amounts of other gases. But those gas molecules are floating around in the atmosphere. This radiation comes from the sun, hits one of the gas molecules, and it splits the electrons off from the protons. So you get the electrons, which are negatively charged, and the protons, which are positively charged. And starting at 30 miles above the surface of the Earth, the molecules are far enough apart that those ions can separate, and you get ionization. The further you go, the higher you get, the further apart the molecules are, so that the ions actually get split further apart. When the molecules are close to the Earth, then it's very easy for those molecules to come back together, the positive and negative ions to come back together. The further away from the Earth, the further apart the ions are, and the less quickly they come back together. The ionization, therefore, becomes a weak conductor. It actually conducts electricity. And the D layer starts at 30 miles above the Earth, and it goes to about 60 miles. The E layer is in the 60 to 70 mile range. And then the F layer, actually, there's an F1 layer and an F2 layer. The F1 layer is between 100 and 140 miles above the Earth, and the F2 layer is 200 to 300 miles above the Earth. At nighttime, the F1 and F2 layers come together to form a single F layer. Now, the D layer is not our friend. The D layer, where's Jeff? What do I call the D layer? The darn D layer. That darn D layer absorbs radio signals. So it reduces the ability to talk long distance on the higher frequencies. It absorbs the radio signals. So it's that darn D layer. That's how I just like you to remember it. The E layer has some properties of the D layer, but also it does have some refracting capability, particularly to refract some of the higher frequencies. And then the F layer is what we really use when we talk about HF propagation or skywave propagation. The D layer, because the molecules of gas are so close together, is only present while it is being actively ionized. So as long as UV radiation is hitting it, or the ionizing radiation is hitting it, you're going to get ionization. The D layer will be ionized. When the sun is not present, the molecules come back together, they collapse, and you no longer have the D layer. So the only time the D layer is present is during the day. It disappears at night. Let's leave the slides up. It disappears at night because the ions and the free electrons are close enough that they recombine quickly when no UV ionizing radiation is present, and they return to a neutral condition. So at night, the D and E regions disappear, and the F1 and F2 regions combine to form a single layer. But the F layer can actually be present even when it's not being ionized. So on the dark side of the Earth, you can still have ionization in the F layer. As I said, the E layer is 60 to 70 miles above the Earth. It acts similar to the D layer. It's higher and less dense than the D region, and it can last longer after sunset. Not much longer, but it will last a little bit longer. And the F layer is the least dense of the three. It's between 100 and 300 miles, and it will stay present even when it's not being actively ionized. So it will remain partially ionized at night. During the day, the F layer will actually split into an F1, which is a lower layer, and an F2, which is a higher layer. And the height of that F region depends upon the current time, the season, whether you're summer or winter, what your latitude is, how high you are above the equator, and what the solar activity is. And we'll be talking about solar activity shortly. At any particular location on the face of the Earth, the stronger the illumination from the sun, the higher the F2 layer will be, so the maximum height is going to be reached when the sun is directly overhead at noon. Okay? Does that make sense? Now, the ionosphere is a weak conductor. It tends to refract, not reflect. It tends to refract radio waves. The amount of refraction depends upon how much ionization is occurring and what the frequency is. The higher the frequency, the more likely that the radio wave will pass through the ionosphere. So let's think about this for a minute. The HF frequencies go from 160 meters to 10 meters, right? When you get above 10 meters, we go into VHF area, 6 meters, 2 meters, 440. Well, 2 meters have a short wavelength, where 80 meters have a really long wavelength, okay? So let's just talk about 20 meters. That's, 66 feet in length. So from the peak to the trough of the wave, remember it's a sine wave, from the peak to the trough is 66 feet. 2 meters is 6.5 feet in distance. So from the peak to the trough, it's 6.5 feet. Well, that shorter wavelength punches in between those ions. It won't get reflected because it's too narrow a wavelength. It's a short wavelength, so it punches right through. Where the longer wavelength, say 20 meters, which is a 66 feet wavelength, is going to tend to hit one of those ions and get refracted or bent back to Earth. The higher the ionization, the more refraction you're going to have. The lower the frequency, the more refraction. Again, because the lower the frequency is, the longer the wavelength. The longer the wavelength, the more likely it is either the peak or trough or part of that sine wave is going to hit one of those ions. Does that make sense? HF signals will have pretty good refraction. They get reflected back to Earth. VHF and UHF signals essentially have no refraction because they're short wavelengths and they tend to punch right through between those ion separations. Does that sort of make sense to everybody? Okay. Each reflection off of the ionosphere is called a hop, and it allows the signals to be heard hundreds to thousands of miles away. This is called skywave propagation, and we also refer to it as skip. The higher the region that the reflection takes place, then the longer the hop. So if I'm coming off of the F1 layer at 300 miles above the Earth, I'm going to have a further hop than if I'm coming off the F1 layer at 100 miles above the Earth. Does that make sense? Waves that are reflected from the F2 layer can travel up to 2,500 miles before they return to ground. Well, now there's much more than 2,500 miles. So for instance, if I talk from here to the Antarctic Scientific Station, that's about 7,000 miles. How the heck did I get there if each hop is only 2,500 feet? 2,500 miles, I mean. Well, it's probably multiple reflections. So my signal goes up, hits the ionosphere, comes down, hits the ocean, which is a good conductor because it's salt water, goes back up, comes back down another 2,500 miles, goes back up, comes back down another 2,500 miles. So oftentimes you'll have several hops between two different stations in order for HF propagation to occur. In fact, a total of about 7 hops will let the signal come all the way around the Earth, and sometimes you can actually hear an echo of your own signal if you've got really good propagation, and propagation is excellent. Unfortunately, for the past month or so, propagation has been kind of as any of y'all have been on HF are aware. The hops from the E layer are shorter, only about 1,200 miles, because the E layer is lower, right? Makes sense. You've got to have the proper combination of frequency and the amount of ionization, and it has to be a low enough angle for the bending to recur and come back to Earth. The highest, and I'm going to show you an example of this in a second, the highest takeoff angle that will get reflected back to Earth for any particular frequency is known as the critical angle. So for instance, if I'm on 20 meters, say 14.300 megahertz, if I send the signal off at a 40-degree angle, it will be reflected. If I send it off at a 75-degree angle, it may not be reflected. It may pass on through the ionosphere and travel on out to space. And I'll give you an example of that here in a second. So here's my transmitting station up in the northwest, and if I come off at an angle here, say about 30 degrees, it gets reflected and comes back down to a station over here in Europe. If I take a look at what the critical angle is for this particular frequency and this particular amount of ionization, let's say the takeoff, the critical angle is 45 degrees. Well, any signal that comes off at 45 degrees or less, say 30 degrees or 15 degrees, will be reflected back to Earth. If the angle is higher than 45 degrees, if that's the critical angle, then it doesn't get reflected and actually travels off into outer space. Does that make sense? Because it's punching through. It's punching through. It doesn't have enough of the ions that are apart that are reflecting it and conducting it. The critical angle is the highest angle at which a wave can be returned to Earth. And the critical frequency is something that's important. It is the highest frequency on which a wave that's transmitted straight up will be returned to Earth. And the critical frequency is generally 8 megahertz or less. And that's how we are able to use a transmission form called NVIS, or Near Vertical Incident Skywave, and I'll talk about that in just a minute. So let's talk about that darn D layer. The enemy of propagation is absorption, and unfortunately that's what the D layer tends to do. In the D and E regions, waves that go through the denser gas, because they're closer together, get absorbed. That D layer is the darn D layer. In HF bands below 10 megahertz, say 40 meters, 80 meters, 160 meters, at AM broadcast bands that you listen to the AM radio, WLS and all those, and at lower frequency, the D region completely absorbs the radio waves during the day, preventing those waves from returning to Earth. How many of y'all grew up listening to AM radio at night when you were a kid, right? So during the day, you couldn't hear it. WLS is in Chicago. It's one of the big nighttime radios. You could hear it at nighttime, couldn't hear it at all during the day because the D layer was present. As soon as the nighttime comes, the D layer is not there anymore, then you suddenly started hearing WLS. The absorption increases in the daytime when the solar UV is more intense. So what is the best time to transmit on HF below 10 megahertz? Well, it's going to be at night, right? Makes sense. That's why we tend to use 40, 80, and 160 meters at night. So let's talk about another enemy of our shortwave propagation, which is going to be noise. The noise covers up weak signals. Remember, what we want to do is improve our signal-to-noise ratio, the SNR. One way you can do that is increase your signal, that is using an amplifier, hats off to Jack Cox, right? Or we can reduce the noise, so we improve the signal-to-noise ratio. So this is a fairly quiet room. If I were to whisper, you could probably still hear me, right? But if we were in the middle of Titans football stadium during one of the last games in the season, I'd have to even be shouting like this for you to be able to hear me back over there, right? Because the noise in the Titan stadium was much higher and the noise here is much lower. So in reality, the best way to improve your reception by improving your signal to noise ratio is trying to reduce the noise. Try to reduce the noise. That's what I really want you to do. The noise is stronger at frequencies below VHF because of atmospheric disturbances, QRN, thunderstorms, and that sort of thing. The lower in frequency you go, the stronger the noise or static. During field day, how many of y'all listened to 80 meters? It's kind of noisy, wasn't it? 80 meters was noisy, particularly in the summer. There's a lot more thunderstorms occurring, and you'll get the static from those thunderstorms real easily. It tends to vary seasonally, as I mentioned. And it's loudest in the summer when the atmospheric noise is strongest. So one other thing we need to think about is what we call long path and short path. Most of our communication occurs over the short path, that is, the shortest distance between 2 points on the outside of the globe. And that may be the polar pathway, for instance. Like to go from here to Russia, if I want to talk from Nashville to Russia, I'm actually going over the North Pole to get to Russia rather than heading east, because the fastest way on a globe, on an orb, is the northern route. Sometimes, however, you may want to go long path, where if I'm trying to talk from here to here, the shortest path is from here to here, but there may not be any ionization on this side. Ionization may all occur around the backside, which is what we call long path propagation. So sometimes the propagation is better the long way around than the short wave around. Does that make sense? Depends on where the sun is. When the short path does not support propagation, sometimes that long path will. And occasionally you will get propagation over both pathways. And if that occurs, then you'll tend to hear a little bit of an echo. The signal will be delayed coming along the long path as opposed to where it's going on the short path. And the station receiving it will hear an echo because it'll be coming about 0.7 of a second difference. I'm sorry, 1/7 of a second difference. And in fact, around the world propagation, you can hear your own signal coming around the world occasionally 1/7 of a second later. And the way we get that is the distance around the world is 250,000 miles. And we know that light travels at 186,000 miles per second. So 25 into 186 is 1/7. Does that make sense? Okay. One thing that we are fortunate right now is that we are in a good sunspot cycle. We've got good numbers of our sunspots. Looked it up today, and the sunspot number was like 160, something like that, which should be good. Propagation has not been that good, however, for the past month or so. There's been a lot of solar flares and some bad solar storms that have been disrupting it. How would a solar storm disrupt skywave propagation? It would tend to ionize that darn D layer, right? So when the darn D layer gets ionized, propagation tends to get worse. So we know that there are sunspot cycles. And remember, the ionosphere is ionized by the ultraviolet radiation coming from the sun. And much of the variation in ultraviolet radiation is due to sunspot activity. 6 or 7 years ago, the sunspot activity was 0, right? Now it's about 160. One sunspot cycle lasts 11 years. So every 11 years, you get this variation in the sunspot cycle, in the number of sunspots, where you get the troughs and the peaks. When more sunspots are observed, more ultraviolet radiation or ionizing radiation is generated. It improves ionization, and you get better propagation in the higher frequencies above 10 megahertz. In fact, even getting into the VHF range, sometimes you get 6-meter skywave propagation. Rarely there can be 2-meter skywave propagation if ionization is strong enough. At the peak of the cycle, you can have enough ionization that 10 meters, 28 megahertz, can stay open for long distance contacts at night. In fact, if you think back 22, 23 years ago when we were at really the height of the sunspot cycle in the mid-90s, let's say, you could be in a car with a 10-meter radio in your car going to work and talking to somebody in Japan with a 10-meter radio in your car. You guys remember that? High ionization negatively impacts the low frequency bands because it activates that darn D layer. So 80 and 160 meters is actually going to have less propagation when you get high ionization because the ionization starts affecting the D layer. When solar activity is low, there's less ionization of the D layer, and you get better propagation on the lower bands, worse propagation on the higher bands. Because the higher bands, the 20 megahertz and above, it's 15 meters and up, they're a short enough wavelength that they may punch right through the ion layer. Does that make sense? One band that seems to do pretty well at all the time is 20 meters. 20 meters is sort of the workhorse band that we tend to use. So if we take a look at daytime and nighttime propagation, basically 160, 80, and 60 meters, the lower frequencies we're going to use at night. 40 and 30, you're going to get a little bit better further distance. But 20 and 17, we're going to really be going long distance. And then the high frequencies, the 10 meters, 12 meters, and 15 meters, those are going to be long distance, primarily during high ionization activity after sunrise. The other thing for us to remember is that the sunspots rotate around the surface of the sun. The sun rotates around its own axis every 28 days. We rotate around our axis in 24 hours. For the sun, it takes 28 days. So every 28 days, the number of sunspots that are facing us is going to tend to repeat. So if you want to look at what you're going to have in terms of propagation tomorrow, or a good idea, let's say you wanted to look at what your propagation was going to be like at field day. Take a look at what propagation was like 28 days before field day, and it's going to tend to be about the same because the sun is rotating and you'll have the same number of sunspots facing you every 28 days. One way that we can measure solar activity is to measure sunspot number, and the sunspot number is also fairly equivalent to the solar flux index. This is a slide that shows the solar flux index, which is the amount of 2800 megahertz radio energy coming down, and as the solar flux index goes up, the number of sunspots go up. So right now, our sunspot number was about 160. We'll look that up in a minute, but that's what it was when I last checked. And so you've got pretty good number of sunspots and pretty high solar flux index. Another thing we look at that you can get reports at would be the K index and the A index, which is a measure of the geomagnetic force going around the Earth. And the A index is basically an average of the previous 8 or 9 K indices. And in fact, this solar propagation is so important, it is reported worldwide. If you look at QRZ, and I'll bring that up in a minute, there's actually a little blurb on QRZ webpage that shows you what the current solar activity is. There's plenty of places on the web that you can find it. A couple of other things I want to talk about is the MUF and the LUF. The maximum usable frequency is the highest frequency of propagation that will occur between 2 points. And it's going to be dependent upon the time of day, the amount of ionization that you have, where those 2 points are located. So a good example, I was working the 10-meter contest back in December, and you could tell where there was propagation and where there wasn't propagation. So first thing in the morning, 8 or 9 o'clock in the morning, I could work to the east because the sun was already over there. I couldn't work anything to the west, so I wasn't working any West Coast stations or any Japanese stations. So if I took a look at what the maximum usable frequency was between me and Tokyo, at 9 o'clock in the morning in December, the maximum usable frequency was about 6 megahertz. So below, below 40 meters. So I could probably work them on 80 meters or 60 meters, but certainly not be able to work them on 20 meters or 10 meters. But I was able, the maximum usable frequency going from here to Rhode Island was 30 megahertz, so I could work them on 10 meters without any problem. So the maximum usable frequency is the highest frequency at which propagation exists between 2 points. The lowest usable frequency is the lowest frequency that you can use, because below that, the signal will be absorbed by what? The D layer, the darn D layer. To get the best long wave propagation, what you want to do is take a look at the distance between those 2 points, and you want to use a frequency as close to the maximum usable frequency as possible, because that is going to tend to punch through the D layer better, and you'll have low angle propagation and low angle reflection. So, for instance, if I am shooting my signal at 45 degrees and it goes up 300 miles and comes back down, it may come down only 800, 900 miles away. On the other hand, if I aim my signal out at an 18-degree angle, it'll go out until it hits 300 miles away, and it may come down 2,500 miles away. Does that make sense? Because here the angle is going to go up and down, here the angle will go way out and then down. So low angle takeoff is what you want if you really want to use long distance propagation. The MUF and LUF are going to depend upon the specific paths between those 2 points, and it varies depending upon the time of day, season, and the amount of ionizing radiation that's present. You want to operate near the maximum usable frequency to get excellent results, because absorption is going to be less there. Does that make sense? One way to check it is to listen for the propagation beacons. And, there's bunches of propagation beacons. You can go to the North California DX Foundation, ncdx.org on the web, and you can actually listen to the beacons themselves. Turn your radio to the beacon frequency, and you can listen and see if your station has that actual propagation occurring. You've got to use a frequency between the lowest usable frequency and the maximum usable frequency in order to make contact with a different station. And that's what we call a circuit. From here, like I may have an open circuit on 14.2 megahertz from here to Spain, but I won't have an open circuit from here to Spain on 28.2 megahertz. Does that make sense? Because I want to be below the maximum usable frequency, but above the lowest usable frequency. All right, now this is probably what's been going on for the past month or so with solar disturbances. When we have a solar flare that occurs on the sun, about 8 minutes later, the radiation from the flare reaches the Earth. So this is traveling at the speed of light, because the sun is 8 light minutes away from us. It's traveling at the speed of light, and you can get massive ionization of the D layer, which is going to do what? It's going to shut down skywave propagation. It'll shut down skywave propagation. This eruption of energy in solar material when the magnetic field disruptions occur on the surface of the sun. Another thing you can get is a coronal hole. You can get plasma, which is actually matter that travels to Earth, what we call a CME, a coronal mass ejection. That takes anywhere from 20 to 40 hours to travel, because it's not traveling at the speed of light, because it's actually matter rather than radiation that's traveling to the Earth. A coronal mass ejection. All of these disrupt HF propagation. Now, when do these disrupt HF propagation? Only during active ionization. So they disrupt HF propagation only during the day. They don't disrupt HF propagation if both stations are not in sunlight. So if they're on the dark side of the Earth, away from the sun, HF propagation is not disrupted because of these. Does that make sense? Sudden ionospheric disruptions or disturbances occur when you get this radiation from the solar flare, travels at the speed of light, hits us 8 minutes later. It increases absorption in that darn D layer. Everybody's going to remember the darn D layer, aren't they? Jeff, you remember that when I talked about this about 10 years ago? Okay. When you get this absorption, you can get a radial blackout. But the radial blackout only occurs at daytime. It does not occur at night. So it only affects the sunlit side of the Earth. Dark side communications may be relatively unaffected. Does that make sense? Also, another thing we can get is geomagnetic disturbances. It's an interaction between solar wind and the geomagnetic field on Earth that can affect regions of space called the magnetosphere. And when we get these coronal mass ejections that reach Earth 20 to 40 hours later, we can get all sorts of things disrupting ionization in the E layer. We can get aurora, the aurora borealis, and I can't pronounce this word, but the aurora on the southern, it's aurora australis, or it's the aurora over the southern hemisphere, but I just can't pronounce the word, so bear with me on that. Long distance paths that go over high latitudes, particularly those that pass near the poles, may be completely wiped out for hours to days because of the magnetosphere is attracting that material towards the poles. That's the same thing. Now, on the other hand, the aurora, you can get auroral propagation, particularly on the VHF and UHF bands. So you can actually aim your directional VHF antenna towards the auroral curtain, and you may be able to bounce off the aurora borealis or the aurora australis. Does anybody know how to pronounce that word? Australis? Australis? Okay. Thank you. Australis. For some reason, I just can't get it out there. They create the auroras that can reflect radio waves in the VHF range. And it can be strongest on 2 meters and 6 meters, and you tend to get modulating signals like a hiss or a buzz. All right, we're almost done, just 4 slides left. I'm going to talk about scatter modes. So we can actually get some, in addition to reflection, where it bounces like a mirror, we can get some backscatter because we will get reflections from features on the Earth's surface. The waves can be scattered from within the ionosphere, allowing signals that are too far to be heard by ground wave propagation, but too short to be heard from skywave propagation. So you're in that skip zone, and that backscatter will allow you to fill into the skip zone where it may not be heard otherwise. So let me give you a good example. Let's say I've got skywave propagation, I'm hitting the F2 layer, and I'm able to talk to this station over here. If I did not have any backscatter, this receiving station in the middle here that I'm highlighting would not be able to hear this station or this station because it's in the relative skip zone. It's too far away for ground wave signals to be heard and too close for skywave signals to be heard because the skywave signal is going to reflect over here. But you do get some backscatter off of the F layer and the E layer, and this receiving station may be able to hear some very weak signals because of this backscatter in the relative skip zone. Does that make sense? Another thing we talked about earlier was NVIS, or near vertical incident skywave propagation. At signals below the critical frequency. Now remember, the critical frequency is the frequency at which if I shoot the signal straight up, it will be reflected down to Earth. So signals that reflect, even if I send them vertically up, will be reflected if it's below the critical frequency. Critical frequency is usually below 8 megahertz, somewhere between 5 and 8 megahertz. So usually the critical frequency, 80 meters you're going to be able to get NVIS, 40 meters sometimes you're going to be able to get NVIS, 20 meters you're not going to have any NVIS. Why? Because the 20-meter signal, if you send it straight up, is going to punch right through the ionosphere. I was listening on the repeater several years ago, and actually it was not this repeater, it was a different repeater, so I'm not going to be pointing at anybody, but it was a repeater outside of Williamson County I was listening on, and these guys were pontificating about building an NVIS antenna for 20 meters. And I'm thinking, dude, that ain't going to work. You're not going to get, you do not get near vertical incident skywave propagation on 20 meters. Signal's going to go straight through the ionosphere. You will get it. It's almost like taking a spotlight and shining it straight up when there's a low cloud layer, and I aim that spotlight straight up. The low cloud layer reflects it, and you get a nice cover of your radiation in a circle around your area. So on 80 meters, which is below the critical frequency, if I send it up vertically by having a low altitude antenna, say about 1/10 to 1/4 of a wave above the ground, where most of the signal goes straight up, it will be reflected around a 200 to 300 mile range around my transmitting signal. And that's perfect for close-in communication. So again, here it's NVIS is a frequency that gets reflected back within 200 to 300 miles of our area. What you want to do is place your horizontally phased dipole low to the ground, generally 1/10 of a wavelength above the ground. So 80 meters, you want to put it 8 meters above the ground, 24 feet, 25 feet. So an 80 meter antenna at 25 to 30 feet is going to be an NVIS antenna, right? And here's how it works. Signal goes straight up, comes right back down. Straight up, comes back down. Generally within about a 300 mile range. All right, well, that is the end of my propagation talk. I'll be happy to entertain any questions. Yes?
20 meters is possibly negative.
Great. Let me repeat the question so everybody...
So my question is strong as ground wave.
Exactly. Now, that's one thing about ground wave. The question was about ground wave propagation on 20 meters, ground wave propagation 80 meters versus near vertical incident and above. So one thing, the higher your frequency is, going from 80 meters to 20 meters, there's more absorption in ground wave. If you think about it, you've got the peak and trough are hitting the ground more frequently, so you're going to tend to get more absorption on ground wave the higher the frequency is. Now, the question you brought up was about vertical antennas versus a horizontal dipole. Vertical antenna has a takeoff angle of about 17 to 18 degrees, where a horizontal dipole has a takeoff angle of 30 to 35 degrees. So one thing with the vertical antenna, your takeoff angle is going to be a little bit lower. You will get some absorption, but there is some decent ground wave propagation on 20 meters, although the ground wave propagation on 20 meters is going to be less than the ground wave propagation on 80 meters, only because you get more absorption on 20 meters at ground wave. You can do it. If I was going to, and I mean, it is possible to get there, but I think if you're going to get close-in propagation, do you want to do it within a 20 to 40 mile range or a 200 to 300 mile range? I think that's going to be the question there.
Yeah, let's have a
Exactly.
neighborhood conversation in Europe.
Yeah, exactly. Just have it local. All right, any other questions?
Yeah.
Yes.
So starting this spring, we've been seeing significant signal. Anyway, from a S9 signal, talking to someone, it'll get to a 4 or 5 and then back up. Why are you seeing
A lot of fading of your signals. I think we've had a lot of ionospheric disturbances related to solar flares. The solar flare activity I was reading has actually gone up quite a lot. If you go to the ARRL website, there is a solar weather area of the ARRL website. I think it's n7us.com. He does one of the solar weather columns for QST, and he was talking about the solar flares being really problematic. And I think that's what the issue is. The solar flares ionizing that darn D layer, and so you get reduction because of absorption from the D layer. Great question.
Okay, I'm having a horrible time right now working polar station.
Yeah, go to higher frequencies. See if you can use a higher frequency.
I was on, I guess, one of my stopped working in Italian park. So I thought, well, let's leave the Italian.
Working in Italian part? You said an Italian park? Nice, nice. Paul, you had a question?
What was the comment? You had commented about North California DX Foundation. There's actually, it's an app for that. You can, and it will tell you what frequency they're on, what news broadcasting. So if you continue to radio to that frequency, you can, if you can hear them, then you know the propagation.
Yeah, in fact, let me show you here, North California DXFoundation.org. And then you go to beacons here, and then, I'm sorry. Oh, darn it. Yeah, that darn D-layers. Anyway, but if this is the website, and they'll show you the beacons coming up individually. Also, one other thing, let me show you. Remember I said on the QRZ webpage, right here is your solar information. So the solar flux index is 156 and sunspot number is 187. And it'll tell you, what bands have good day propagation and good night propagation. And that's on QRZ.